Okay.
Okay, you see, go through the question first of all. Page number 47, exercise problem 1.14, which states that the figure 1.33 shows the tracks of three charged particles in a uniform electrostatic field. Give the signs of three charges. Which particle has the highest charge to mass ratio? See, when you are looking at the diagram, the electrical field is provided by two plates, the top plate and the bottom plate. The top plate having the positive charges and the bottom plate as having the negative charges. The charges are moving from the top plate to bottom plate because the electrical field is from positive charge to negative charge. Then when you are considering the three paths inside the electrical field, two paths which are deflected towards the positive charge represent that the two charges are negative in nature, and in the third path the particle is deflected towards the negatively charged plate. So the particle in the third path should have a positive charge. Now what it is asked, you are asked to calculate charge to mass ratio. Which of the charge to mass ratio is having the highest value? So charge to mass ratio is E by M. Since it should be highest, we have to calculate which one is having E by M maximum. So let us consider like this. We know that according to equations of motion, S is equal to ut plus of at square. Here S is the vertical displacement produced, that is taken to be y. Then initial vertical velocity is 0. So u equal to 0. Therefore, the above equation becomes y is equal to half into a into t square. What is a? A is the acceleration that was being produced on the charged particle, which can be calculated using this method. That is, electron moving the charge q, not E. The charge E moving in an electrical field experiences a force. The force experiences E into E. So force can be written as mass into acceleration. So acceleration can be written as A into E divided by M. Substituting in the equation, we get y is equal to half into E by M into t square. On simplifying this or on rewriting this, we can write this as half into E by M into t square. All these quantities, this half, this applied electrical field, and the time taken for the charged particle to cross the electrical field, since all these are constants, we can state as the amount of deflection produced y is directly proportional to the specific charge. So from this specific charge or E by M, this E by M charge to mass ratio will be maximum if the amount of deflection produced is also maximum, since both are directly proportional. So from figure, the particle moving in the path 3 has the maximum deflection. We can write from the figure, the charged particle moving in the figure 3 has the maximum deflection. So the value of E divided by M, charge to mass ratio, is maximum for the particle in the figure 3. So the answer is the third one. See the problem number 1.15. Come on, let us go through the problem. Consider a uniform electric field E, which is equal to 3 into 10 to the power of 3 I Newton per coulomb. That is, I cap represents it is acting along the x-axis.
Exactly.
So let us consider the electrical field E. Electrical field E vector is 3 into 10 to the
And
power of 3
three.
I cap Newton per coulomb, which is representing I cap represents the electrical field is acting along what? The electrical field is
Exactly.
acting along the x-axis. Okay. Then what is the flux of this field through a square of 10 centimeter on a side whose plane is parallel to YZ plane? Then the second one, what is the flux through the same square if the normal to the plane makes an angle 60 degree with the x-axis. First of all, let us consider the first one. What is the first one? See, what is the flux of this field through a square? So inside this, you are having a square. Okay, you are having a square whose plane is, it was given like this. See, square of side 10 centimeter or whose plane is parallel to YZ plane. Plane is parallel to YZ plane means the normal drawn to the plane and the electrical field, that is dA vector is the normal drawn to the plane and E vector is the electrical field. Both are considered to be parallel. So theta equal to 0. If theta equal to 0, they have asked what is the flux. So when you are considering the first one A is given as closed integral of E into ds into or dA into cos theta. That is the formula. So the flux available phi is equal to the applied electrical field is constant. Integral of ds will be fetching you the total area A into cos theta. So in the first concept, we have represented theta as 0. So we can consider phi is equal to, what is the electrical field? 3 into 10 to the power of 3 into, what is area? Area is side into side. Let us calculate here. Area A equal to side into side. What is the side? Side is A into A. What is A? It was given it out as 10 centimeter. So I can write 10 into 10 power minus 2 into 10 into 10 power minus 2. So I can write 100 into 10 power minus 4, which can be written as 10 power minus 2 meters square as its area. Substituting here, area can be written as 10 power minus 2 multiplied cos theta. Since theta is 0, cos theta equal to 1. So substituting here, the value of flux will be equal to 3 into 10 to the power of 1 Newton meter square per coulomb. Or I can write phi is equal to 30. 3 into 10 power 1. It is 30 Newton meter square per coulomb. This is the first one. What is the second option? You see, what is the flux through the same square? So flux is asked. You are asked to calculate flux through the same square of side 10 centimeter. If the normal to the plane makes an angle 60 degree with the x-axis. So along the x-axis, you are having the electrical field. When you are dropping the normal to the square, that is ds vector, is inclined at an angle 60 degree. So theta equal to 60 degree. As we know, theta is angle between the normal drawn and the electrical field. So electrical field is along the x-axis since it is given as I cap, and the normal drawn to the square is at an angle of 60 degree with the x-axis. So theta equal to 60. If that is the case, cos 60 or cos theta is equal to 1 divided by 2. So what is the value of flux then? The value of flux is again the same formula, closed integral of E into ds into cos theta. So electrical field E is a constant, area A into cos 60. Substitute E is 3 into 10 to the power of 3. Area is 10 power minus 2. Cos theta is 1 by 2. So when you are subtracting, you will be getting when you are dividing 2 and 3, we can get 1.5 multiplied it with 10, which is equal to 15 Newton meter square per coulomb. That is the answer for the question number 1.15. Let us go for the problem number 1.16. What is the net flux in an uniform electrical field of exercise 1.15 through a cube of 20 centimeter so that its faces are parallel to the coordinate planes? See what it is given. What is the net flux of the uniform electrical field of the exercise 1.15 through a cube of side 20 centimeter oriented so that its phases are parallel to that of the coordinate axis. Let us draw a diagram. See, according to the problem given, the electrical field is acting along the x-axis, which is represented as E, which is equal to 3 into 10 to the power of 3 I cap Newton per coulomb. Since it is given as I cap, I have drawn it along the parallel. Now I have considered a cube which is having a side of about 20 centimeter placed parallel to the coordinate axis. Now, when you are considering the net flux through the cube is equal to 0. This is taken to be the answer. Why? Because when you are considering this cube, let us take the x-axis alone. On one face of the cube, isn't it? You have to calculate the area. Then only you can able to calculate the flux. What is flux? Flux is equal to closed integral of E into ds into cos theta. See, the normal drawn and the electrical field are considered to be parallel. So cos 0 equal to 1. So flux available is equal to closed integral of E into ds, or you can write flux available is equal to E into A. So when you are considering the left-hand side face, the flux is entering. What is meant by flux? Flux is nothing but total number of electrical lines. Total number of electrical lines through the given area. That is the meaning for flux, through the given area. So when you are considering one edge, one face of this cube, on the left face, the total flux or the number of electrical lines entering is equal to the number of lines that is leaving on the other side. So we can say that what? So we can say that the flux entering the cube is equal to the flux leaving the cube. We are saying the total flux available is equal to what? The total flux available is equal to another. See, let us consider another question, one more question, an extra question. You can take this question. What is the flux through any one face of the cube when it is placed inside an uniform electric field? So if that is the case, the flux available is equal to Q divided by, that is when you are considering Gauss law. According to Gauss law, the flux available Q is equal to Q by epsilon 0. This is according to what? This is according to Gauss law. But when you are considering about the cube is said to have how many phases? Said to have 6 phases. So we can write what we can write, the flux through any one of the phase. So the flux through any one of the phase, is phi is equal to Q divided by 6 epsilon 0 as its answer. Let us read the problem. Careful measurement of electrical field at the surface of a black box indicates that net outward flux through the surface of the box is 8 into 10 to the power of 13 Newton meter square per coulomb. What are the questions asked? What is the net charge inside the box? The second one, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or not? Or why not? We have to say the reason. First of all, let us go through the problem again. Careful measurement of electrical field at the surface of a black box indicates that the net outward flux. So what it is given? The given is net outward flux is being given. Net outward flux. Net outward flux, let us consider it as 5. And this was being given as 8 into 10 to the power of 13 Newton meter square per coulomb. What it is asked, what is the net charge inside the box? That is the first concept asked. So A is, you are asked to calculate what is the net charge available. So when you are considering flux phi, according to Gauss law, flux phi is equal to Q divided by epsilon 0. This is according to what? According to the Gauss law. If that is the case, I can calculate the value of Q. What is Q? Q is equal to 5 into epsilon 0. What is 5? It is 8 into 10 to the power of 13 multiplied with 8.854 into 10 to the power of minus 12. So when you are
8 into 10 power 3
3 தான் கொடுத்திருக்கா. Okay, let us take it out as 3 then. ஒரு சின்ன doubt தான் எனக்கும். Okay, let us consider. This was being given as 3. Okay, so 8 into 10 to the power of 3. Here also then 8 into 10 to the power of 3. So what will be your answer? Into 10 to the power of minus 9. So 8.854 multiplied with 8, you will be able to get 7.08. Isn't it? 7.08. So you will be getting the answer as 7.08 into 10 to the power of minus 8. I think so. You just multiply it, then you can able to get the answer. So when you are multiplying, here you are having 10 power 3, here you are having 10 power minus 12. So that it is 10 power minus 9. When you are multiplying, 8 4s are 32, again 3, 8 5s are 40, so 43, 4, 64 plus 4, 68, again 6, 8 into 8, 64, 64 plus 6, you will be getting 72. So you will be getting 72.832 into 10 power minus 9 coulomb, or I can write like this, 7.2, isn't it? 7.2 into 7.2832 into 10 to the power of minus 8, or I can write like this, 72.8 nano coulomb. Am I correct?
10 power
Okay.
minus 6.
If you want to write it in this in terms of 10 power minus 6.
Sir, 728.32.
No, sir. Minus 8 means you have to go in the other side. 0.0728 into 10 to the power of minus 6 coulomb. Or I can write 0.728 microcoulomb as the answer. Either I can say the answer in nanocoulomb or in coulomb like this, 72.832 into 10 power minus 9 coulomb. Or I can write Q equal to 72.8 nanocoulomb. Or I can write Q equal to 0.0728 microcoulomb as the answer. See, the question is, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? No, we can't conclude. We cannot conclude that. We cannot conclude that the total charge, we cannot conclude that the total charge inside the box or inside the black box, inside box as 0. It may 0 or may not be 0. Not charge inside may be 0. Okay, the next one. Why? Why it is so? That is, there may be equal number of positive and negative charges present inside the box. See, if that is the case, equal number of positive and negative charges present inside the box means, according to the additive nature of the charges, the total charge will become 0. We are having charges, but the net amount of charges is equal to 0. So the amount of negative charges and the amount of positive charges inside the box are equal. You are having charges inside, but what will happen to net charge? Then we will say the net charge may be equal to 0. So the concept is, we can't get the total charge. We can't say that, or we can't come to a conclusion that the total charge inside the box is 0. You see, go through the problem again. A point charge of 10 microcoulomb is at a distance of 5 centimeter directly above the center of the square of side 10 centimeter as shown in the figure. So, hint, according to the hint, think of the square as one face of the cube with edge 10 centimeter. So let us consider like this. You are having an cube. Okay, you are having an cube. So when you are considering the side of the cube is considered to be how much length? It is of 10 centimeter. So from the base, okay, from the base of the cube at a height of 5 centimeter. So this distance is considered to be 5 centimeter, where you are having a charge. The charge placed is taken to be what? Plus 10 microcoulomb. Plus 10 microcoulomb. So what is the flux available at this point? Hint according to hint, okay, according to the hint given, the flux through, okay, the flux through any one face of the cube is, any one face of the cube is phi is equal to q divided by 6 epsilon 0, because according to the Gauss law, the flux available is q by epsilon 0. Since the cube is having 6 phases, through one of the phase is taken to be phi is equal to q by 6 epsilon 0. Use this formula. So we can write phi is equal to q divided by 6 epsilon 0. So flux phi is equal to, what is the value of q? Q is 10 microcoulomb. 10 into 10 to the power of minus 6 divided by 6, 8.854 into 10 to the power of minus 12. So simplify this by, I have simplified this with the help of my calculator, and the answer that I have got is 1.88 into 10 to the power of 5, and the flux in terms of Newton meter square per coulomb. This is the answer that I got. Check it out. A simple problem. A point charge of 2 microcoulomb is at the center of the cubic Gaussian surface 9 centimeter on an edge. What is the electric flux through the surface? See, here also you are considering what? Here also you are considering a cube. But here the charge is not placed inside. Here you just go through the problem again. The charge, a point charge of 2 microcoulomb is at the center of the cubic Gaussian surface. Okay, 2 microcoulomb is placed at the center of the cubic surface, 9 centimeter on the edge. What is the net electrical flux through the surface? That was the question asked. So phi net is asked. You are not asked to calculate any one of the surface. The total flux or net flux available is equal to, according to Gauss law, it is considered to be q divided by epsilon. So if it is for single phase, you divide it with the 6. If it is for net, for all the surface, you calculate the form, use the formula. Phi net is equal to q by epsilon 0. Q is 2 into 10 to the power of minus 6. Epsilon 0 is 8.84 into 10 to the power of minus 12. On simplifying, you can write 2 divided by 8.854 into 10 to the power of 6. When I am simplifying this, I am getting the answer as 2.26 into 10 to the power of 5 Newton meter square per coulomb. See the problem number 1.20. A point charge causes an electrical flux of minus 1 into 10 to the power of 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? The second question, what is the value of point charge? First of all, what it is given? A point charge causes an electrical flux. So what is the given quantity? The given quantity is the flux. What is the flux? Minus 1 into 10 to the power of 3 Newton meter square per coulomb. Okay, to pass through a spherical Gaussian surface of radius. So radius is equal to 10 centimeter, or I can write 10 into 10 to the power of minus 2 meter. Or I can write it out as 0.1 meter. Okay, then what it is asked, if the radius of the Gaussian surface were doubled. So option A, if the radius is doubled, what happens to flux? That is the question. How much the flux would pass through the surface? What happens to flux? The net flux never changes. Flux அப்படின்றது never changes. Why we are saying that flux never changes here? Flux never changes here. See, what is the reason? The flux depends only on the charge, and it is not depends upon what? And it is not depends upon its size. Since it is not depend upon its size, by increasing the radius, the flux never changes. So you write the reason. The net flux depends. Net flux depends only on charge. According to Gauss law, and not on size. So if the radius is doubled, there is no change in flux. Okay. What about the option B, the second subdivision? It is asked.
What is the value?
Subdivision. What is the
Value of the
point charge? So you are asked to calculate the value of point charge. See, we know the flux available phi is equal to Q divided by epsilon 0. So the charge Q is equal to phi into epsilon 0. What is the charge? Charge Q is equal to minus of 1 into 10 to the power of plus 3 multiplied it with 8.854 into 10 to the power of minus 9. So charge Q is equal to minus of 8.854 into 10 to the power of minus 9 coulomb. If it is 10 power minus 9 coulomb, charge can be written as minus of 8.854 nano coulomb as its answer.
Okay.